Okay, so now we want to look at code that I've given you in Google Classroom, retrograde motion, that was written in a previous class. You can load that code right up into MATLAB. If you haven't done so, you probably want to stop the video and do that now. Okay, so let's run this code and see what it does. And this code has many of the features that you're going to want to add to make your orbital program work better. Okay, so first of all, let's see what this does. Let's run it. Okay. All right, so what this is doing is it's plotting what the orbits of the sun, that would be in magenta, look like relative to the Earth, and what the orbit of Mars looks like relative to the Earth, assuming sort of circular orbits for the Earth around the sun and Mars around the sun. So you can see the orbit of Mars relative to the Earth is quite complicated, but that's what astronomers actually see when they look at Mars in the sky. It seems to be leaping forward and then actually moving backwards at part of its orbit because of the Earth's motion around the sun. Okay, so let's analyze this code piece by piece to see how we made this happen. Okay, so first of all, you can see these two numbers here in the parameters are the radius of the Earth as it goes around the sun, and the time it takes the Earth to do that. All right, so you can see this is in days. So 365 and a quarter is an Earth year, which is how long it takes the Earth to go around the sun. Then we put in the numbers for Mars. It is, and we did it in terms of the Earth numbers. Okay, the radius of orbit is about 1.5 times that of the Earth. All right, and the time it takes to go around is almost double that of the Earth. So the Earth and Mars travel around the sun in different amounts of time, so they'll kind of go in and out of sync with each other as they go around the sun. All right, and we're going to plot this for 4 Earth years. That's our T max. And the DT value that we use right now is 7/2. Okay, so that's in days. So each, we're plotting every half week. Okay, so 7/2. 7 would be a full week for a time step, but dividing that in half, we're plotting half weeks of time as we go along. Okay, so you can see in the code, we initialize the vectors for time as usual. Okay, now, notice in this code, the sun is going to go around the Earth. Okay, so we need to get X and Y positions for the sun. We need X and Y positions for the Earth relative to the sun. And then we're going to get X and Y positions for Mars relative to the sun. Okay, so remember the Earth goes in a circle around the sun. So how do we get those positions? So in this code, we're starting by putting the sun in the middle. It's at 0, 0. So the sun's position is starting out as zeros everywhere. Okay. Then these two lines of code take the Earth's radius times the cosine of 2 pi over its period. Okay. So 2 pi over the period gives the angular velocity for the Earth. Okay. Every time T gets to a period or 1 year, 365 and a quarter days, T times this quantity ends up giving you 2 pi, another factor of 2 pi. Okay, so this is 2 pi divided by the period times the time. So this gives all of the x positions. We do the same thing here as the argument of the sine function, and we'll get all the y positions for the Earth relative to the sun. We do the same thing for Mars. We just substitute the radius for Mars and the period that it takes Mars to go around in instead. Now, in order to get all of this to move around the Earth instead, we get new coordinates for the sun by subtracting out the Earth's position. So that will make the sun go around the Earth. Okay. We get new positions for the Earth. Now you can see how this is going to give us nothing but zeros. We're going to take the Earth's X positions and subtract the X positions from it, and its Y positions and subtract the Y positions from it. So all of the Earth's positions will now be zeros. So that's why the Earth stays in the middle when we go to plot it. And we subtract the Earth's location from the points for Mars and the positions for Mars. And so this will give us the position for Mars relative to the Earth by subtracting the Earth's coordinates out. Okay, so this is going to switch everything to the Earth's reference frame simply by subtracting the position of the Earth out from all of the other positions. And so then it puts the Earth at the center of the universe, okay, or center of our solar system. Now we do some plotting, okay. Understanding this plot statement is the key to being able to make many of the improvements, okay. So the plot statement here is plotting one thing, okay, that's the magenta circle. So when we run the code, those would be the points where the sun is, okay. Now you'll notice as it goes around in a circle, we have a trail, a magenta trail. Well, that's this line of code right here. Because what we do is we connect the points for the sun from the first point up to the one we're at. So remember, IT is the one we're on. So we connect the first point up to the one we're on, and that creates a growing trail. The point we're on gets later and later, so that creates the growing trail. Okay, this line of code plots the Earth, a blue circle just in the middle. We don't need to create a trail because it's not going anywhere in this code. Okay, then what do we do with this next line of code? Okay, in this line of code, we're going to plot, we're going to connect right here the Earth points relative to the Earth, okay, to the sun's points, okay, with a magenta line. So when we run the code, you can see a radial line. So at every time, we're connecting the X position of the Earth and the X position of the sun up to the Y position of the Earth and the Y position of the sun. We're just connecting those two coordinates. So notice you put the Earth position in the X direction, the Earth position in the Y direction, and then you put the sun's X coordinate, and the sun's Y coordinate in that order in the code. And you're going to connect those with a magenta line. The next thing we do is we connect Mars position, okay, in the same manner, so that we'll get a connecting line between the Earth and Mars. And I probably should have done this in a different order, okay, because we kind of do this backwards now. This line of code gives the single point. So let me highlight that line of code. For Mars, it's a red circle, okay, it's a single point. And then this line of code gives me the trail for Mars. It's connecting from the first point all the way up to where we are to create the trail, right? And then we square out an axis, all right? And now here is where we create we have a counter up there, a text command, that instead of just giving a number for the time and days, it actually creates a sentence, okay? So the time is a string, okay? It's a sentence, all right? So to concatenate that, okay, notice we have a bracket here inside of the, so we first of all have a parentheses, and then we create a bracket, okay? Notice that's going to kind of set up a matrix of little pieces of string that we're going to stick together, okay? The first string value is this time, and I even included some spaces and an equal sign, and then we're going to convert the time that we're on into a string. That's what num to string does. It converts a number to a string. Floor simply rounds it down. So if it's a fractional day, we don't want to have decimal points in there. So floor just rounds it down to whatever day we're on. Okay, and then this comma is followed by, we're just continuing on to the next line, and we're adding the word days onto the end of the number, right? Then the text command tells us the first two things, tell us where to place it. It's 0 in the X direction, 1.7 times the radius of Mars. Notice that's related to our axis command in the Y direction. And then we'll put the time, which has already been created, into the text command. All right. And then we just square out the axis and put in a draw now command. And that's what makes this code run. Okay, so in this code, you can see we've added growing paths. We've added the locations of points. That's already there, like in your code. We have a growing path, and we have lines connecting points together to give us radial lines. And then we also have this counter that has a sentence up here. And those are the types of features you need to be able to add to your orbital code. The final thing that your orbital code has, notice it ran very slowly. If I wanted to make dt very small, let's make it 0.001 in order to get very precise calculations. You can see that suddenly it's taking way too long to draw all of this. It's not the calculations that are taking too long. What's taking too long are the drawings themselves. So I want to actually stop running that code. Won't let me interrupt it right now. So I'm just going to come back over here. I'm going to pause it. Okay, and I will quit debugging it. Okay, so it'll be ready to run again. Okay, and then if I want to have a very small time step to have accurate calculations, I probably should put in a skip command. So we're going to skip, we'll start by skipping by hundreds, okay, to make it 100 times faster. So this will skip frames of plotting. Now we need to use this skip two places. The first thing we'll do is we'll add it to the for it equals 1 to nt. If I put the word skip in here, it will skip by hundreds of pictures. All right. But the other place we want to use skip is right in this statement here. We've now created so many points that connecting them will take a fair amount of time. So I don't want to connect all the way from 1 to where we are. I want to do that in steps of 100. So I will add skip wherever I'm drawing an animated growing line. Okay, so this will make the line draw much faster. Okay, and we'll have to do the same thing down here where we were going 1 to IT. We'll want to add a skip so that we don't connect the huge number of points that we now have. Okay, so we use skip in the for loop. Whoops, I'm sorry. To skip frames, but we also use a skip down here when we're connecting points. When the number of points is ludicrously large, we want to skip and not try to connect all of the points, or it will take a lot of time. So let me run that again and see how it does. Okay, so it's still going very, very slowly. So how would I correct that? I would want to skip the time, okay, the time is in days. Just plotting it out in days is taking far too long. So I could lower dt. And instead of doing every 10th of a day, okay, I'm sorry, every 1,000th of a day, I might switch it to hundredths of days. Let me pause. Quit debugging, okay, and go back to it and run it again. So dt is smaller, and I'm keeping skip at 100, and let's see what happens now. Now it's a much more reasonable speed. If I wanted to go even faster, though, I could change my skip command to a higher value. So I'm using very, very small time steps, hundreds of days. And you can see the number of days we're using is, we have hundreds of days. So dt equals 0.01 is very, very small. Okay, and we're skipping by hundreds. So it's plotting basically 1 day at a time as we go, and that's a much more reasonable speed to see what's happening.